Hello and welcome to a presentation entitled Integration Factor and First Order Differential Equations Reducible to Exact. We consider the first order differential equation given here y minus y dx plus x dy equals to 0, which you can also express it in other words as dy dx equals to y over x. Looking at the equation in this form, we can actually see that it's an equation which has got a potential to be exact. In this case, our p of xy will be equal to minus y, and q of xy is equal to x. Actually, you must note here that it is actually acceptable to have a function of two variables and it depend on only one variable here. So we can look at this as a function of two variables where only y appears here, and we could assume that there's no term which solely depends on x, but in the x here is actually to the power 0. So we can in that way look at it as a function of two variables. Now, when we now try to test for exactness, we notice that the partial derivative of q with respect to x is equal to 1, and that of p with respect to y is equal to that. So making the equation not exact. We recall that previously we saw functions with which you could multiply an equation like this and turn it to exact. Let's illustrate that once more. And now let's say given that equation with p and q there, and we consider multiplying the equation by a function r of y equals to 1 over y squared. Doing that, we get the equation in this form, and in this form the p of xy becomes 1 minus 1 over y, and the q becomes x over y squared. Having adopted this form of the equation now, we can now test for exactness, and we effectively see that the delta p delta y is equal to 1 over y squared, which is equal to delta q delta x, which actually tells us that the equation is now exact. Now, to go further with that, let's first of all consider these two equations here. We know that if we've got these two equations, if we need to get to a point where we can say x is equals to some value, we actually need factors which used to multiply the equations on both sides in this way. If we multiply the first equation here by 2, we get that x is equal to 6. On the other hand, if we multiply this equation by 1 over 3, we get that the equation, the x is equal to 8. So in this case, the factors chosen here actually act as tools to solve these equations. So they're actually factors which are actually lending us at a solution of the equation. In a similar way, now the integration factor which we've got here, ry equals to that, actually serves to transform the equation into an exact equation, by so doing putting us on a path to be able to solve the exact differential equation, because we've already learned that. So the integration factor actually acts as a tool to transform the equation to exact, then we can solve. And now the question will be, the most question will be, how can we systematically arrive at such functions which transform non-exact differential equation to exact, so that we can solve them. Now, before we can go further with that, I would like to invite you to consider these two functions and also do the calculation to see that these two functions are also integration factors of the same equation. Basically, that telling us that we can actually have more than one integration factor for a given equation. Now, moving forward with our presentation, let's consider the differential equation which has got the potential to be exact in this form. If the equation is not exact, we would need an integration factor to multiply it in order to use the approach we use for exact differential equations. Let us see how we could arrive at an integration factor. Then let's suppose that r of xy is an integration factor for this differential equation. And of course, if it's an integration factor, to transform this equation to exact, it would multiply by r. And once you have multiplied by r, we'll be sure that the equation is exact, like we have seen before. Now multiplying gets us to an equation which we can write in short as rp dx plus rq dy, which will be exact. Now proceeding from here, let's say we've got that equation being exact, which means actually we are claiming that delta rp delta y is equal to delta rq delta x. That's the condition which must be satisfied when such an equation is an exact. In that case, applying product rule on both sides here, considering r and q here as a product of two functions, we can differentiate that using partially with respect to y, and get this kind of a term on the left hand side. And on the right hand side, we are differentiating with respect to x, applying product rule, will get this kind of a term. Now, if at this point here we suppose that the function r is a function of a single variable x, then we will see the following. This r here being differentiated with respect to y will land at 0, and then we're left with this term, and the right hand side here remains exactly the same. And we see that this is equivalent to, if we are regrouping this, this equation is equivalent to r multiplied by delta p delta y minus delta q delta x, which is equal to dr dx. And you note that here I have now denoted that derivative as an ordinary derivative, because of the reason that we have said here that we suppose that r is a function of single variable x, so the derivative can be noted using the ordinary notation there. And then multiplying both sides of this equation by dx dr, we arrive at a simpler expression, which in this case is going to be dr over r equals to this term here, which is in brackets, divided by q dx, because we multiply by dx over qr. So here q simplifies to give us dr over r, and on the other side r simplifies and it will remain with this term divided by q dx. And at that point, I think you can see that on the left hand side we've got a derivative of a linear form, of which we can actually immediately integrate. Then integrating on both sides, we apply the integration signs on both sides there. Then we take this term here in short as r star. And what is r star in this case is actually that term which is in the numerator here. We just try to avoid to make this thing, this expression too crowded, so we write it in short like that way as r star. And then integrating on both sides, we get here ln of r equals to the integral of r star, that again keeping in mind that r star is that. And in this point here, you can see that if we apply e on both sides, we'll basically get the expression for r. And this integration now can be carried out and actually get the final expression of what we're going to use to multiply the differential equation, using that as an integration factor. This is exactly what we get. If we apply e on both sides here, we get r being that. And then this expression, which is here, will be simplified and integrated. Then you will have the expression for the integration factor. So I hope you can see that now we've found a path of landing at an integration factor, at, for now, an integration factor which is dependent on a single variable x. Now, going back to that equation and the equality which gives us that the equation is exact, we know that that equality is equivalent to this one by applying product rule for differentiation on both sides. Now, assuming r is a function of a single variable y, in this expression, we'll land, this expression will transform, will take this kind of a form, doing exactly the same thing, that this 0 is coming out from differentiating r with respect to x. When r is a function of a single variable, then that should be 0. And then following the same kind of thinking we saw before, we arrive at a point that r is equal to e to the power the integral of r star, and now r star is of this form. You'll notice that these two are not it's not exactly what we saw before. We're going to compare them. So in that case now, we now know at least how to find integration factors depending on a single variable, and that is an achievement. We can now given a function and quickly find a way of finding integration factor either in terms of x or in terms of y. We're not actually going to, in this presentation, we're not going to consider the case where the integration factor depends on the two variables for deriving a formula like this. Now, looking at all what we have seen before, we arrive at these two formulae. Check. The integration factor in terms of x is this integral of r star, which is exactly the same as this one. The only difference is the expression for r star. In this case here, we've got delta p delta y minus delta q delta x. I hope you can see here. Try to see how you can remember this. In this case here, remember x dx comes with a p, but p here differential with respect to y. Then we are subtracting the partial derivative of what? Of q with respect to x, and the denominator again is q here. So p is leading here, subtracting the partial derivative of q and the q dividing there. And here we actually just swap around the variables here. We exchange p for q and x for y, and then you've got delta q delta x when here the delta p delta y minus delta p delta y when here we got minus delta q delta x and over p. So I hope you find it easy to remember this kind of formula. This is what we wanted to achieve in this presentation, to find a way that because we're not going always like we've seen in the examples which we've seen before, we're presented with functions which we're supposed to try by multiplying to see whether they transform the differential equation into an exact. But now with this presentation, we've actually arrived at a method, at an approach, a systematic approach to arriving at these type of integration factors. So to consolidate this and familiarize ourselves with the use of this formula, I would encourage you to do the following practice. First of all, we were given this equation, and we saw that these two are integration factors for this equation. Now here what I would like you to do is actually to do the computations according to the formula given here, to actually verify that effectively these are integration factors obtained by using the formula we have seen. And once you've got the integration factors, you can use any one of them to solve the equation to determine the general solution z of xy equals to c. And thirdly, I would like you to determine the unique solution of the differential equation given that y at 1 is equal to 4. I think that is going to be a good way of starting familiarizing yourself with this kind of work. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Sugasfane Msipa.